Okay, let's find out about points, lines, and planes and the things we can do with them. Geometry is a mathematical system that we build by accepting certain facts and basic terms and definitions. We will establish things to be true all the time and we can use them as such. Now, there are some terms that are undefined, such as points, lines, and planes. We'll find out what they are. We need to use these undefined terms to build the definitions of the other figures we're going to use. They're undefined because they're our starting point. We don't have any other words to use yet to describe them, but we will understand what they mean. And here's the basic definition of each. Okay, a point. It indicates a location, a specific location, and there's no size to it. If you keep zooming in on a point, you will never actually see the thing. It doesn't get bigger and bigger and bigger because it's just more precise location in space. Okay, and you can move a little bit to one side and you will be at a different point, a different location. Now, we represent it by a dot and we name it with a capital letter, in this case A. Okay, so lines are represented by straight paths that extend in two opposite directions without end. Okay, this has no end to it, so we indicate arrows on the end saying that just keeps on going forever. Think theoretically here. And it has no thickness, just like a point is infinitely small, so is a line. A line is just the path that connects an infinite series of points all in that same straight path. Okay. Now you can name a line by any 2 points that are on it. In this case, you have A and B on that. And so we can call this line AB. You read this as line AB. If it has a line with 2 arrows over it, line AB. Or BA, line BA, because there's no preferred starting point. You can go either direction. And sometimes you see them named with a lowercase letter such as L here. So we could also call that line L. Otherwise, we would use 2 points that are on it and describe it as I said, line AB or line BA in this case. Now, a plane is the flat surface extends forever, and it also has no thickness. Just like a point or a line, the plane has no thickness. And you can imagine that if you had this universe-sized samurai with an infinitely sharp blade slicing the universe into 2 different sections, that perfectly flat slice along which it's cutting it would be a plane. It extends forever. And you can think of a tabletop or a wall or a floor as a good representation of a partial plane. Now, you can name it with a single capital letter. You can see here that there's no point attached to that P, so that is actually the name of the entire plane. Typically, though, we're going to have 3 unique non-collinear points that are not all in a single line, that when you connect them, you can imagine you connect and you make a triangle. If you extended that flatness of that triangle forever in all directions, that would be the plane. So we need 3 points to describe it, and we can call this then plane ABC, or plane P in this case. That's the idea of our 3 starting point definitions, or terms rather. Okay, so points that all lie on the same line are collinear. They're co meaning they're all sharing, and linear, they're sharing the same line. Okay? Points and lines that lie on the same plane are coplanar. Co meaning sharing, and planar meaning sharing the plane. All the points of a line are coplanar. Since that line is laying on the plane, then all the points in the line are also on the plane. Here we go for problem 1, naming them. What are 2 other ways to name line QT? Now, notice this. Why can figures have more than one name? Lines and planes are made up of many points, so you can choose any 2 on a line or any 3 non-collinear points on a plane and use those to name it. And then points can go in any order. So, looking at this one, what are the 2 other ways to name line QT? You could name it TQ, and you could call it line M because, as you can see, TQ has the lowercase letter m. You could also name it with the point n that's also on that line, so you could call it line NQ, NT, QN, NQ. Okay. What are 2 other ways to name plane P? Well, this is that's not for the point, so how do we name it? We can pick any 3 points on this plane as long as they're not in a line. We cannot pick R, Q, and S. They are collinear. They have to be non-collinear. So 2 other ways would be RQV and are SV. Notice they used V because they can't just use those three. They're all collinear. We could also say QSV. Okay. And what are the names of three collinear points? As I said, we've got R, Q, and S are collinear. You also have T, Q, and N being collinear on this line. Point R, S, and here what are the names of four coplanar points? We have V, R, Q, and S all on the same plane. So R, Q, S, V are all coplanar. Okay, you have a got it problem now. And this is a good time to stop the video and try your hand at these got it problems. Write down your answers and then compare them to the answers when you start the video again. Okay, the three terms that we just talked about and understand point, line, and plane, they're not defined because we would need to have some terms already in order to describe them, give them a formal definition. So we don't have definitions for those. However, we now have an understanding of points, lines, and planes, and we can use those undefined terms to define other terms. And we're going to build now a whole set of terms and ideas from the three starting points, point, line, and plane. So a geometric figure is a set of points. We will describe a circle, a sphere, a line, a segment array, all in terms of points and sets of points, okay? And you'll come to understand that certain things like a circle are just an infinite series of points all equally distant from the same center, okay? Now, space, what is space? Space is the set of all points in 3 dimensions. Essentially, since points are locations, we're talking about, if you talk about all the possible locations you could be in the 3 dimensions, you will be talking about space, all of space. Now, similarly, definitions for segment and array are based on points and lines. Let's look at them here. Okay, a segment is a part of a line. It has 2 endpoints, and then it consists of all the points in between them. So here's segment AB. It's written like this, with a line with no arrows on it, meaning that there's an endpoint here and an endpoint here. Okay, segment AB. You could also start at this end and go to this end, segment BA. But points in between you can't use to name them because you have to be talking about the endpoints only. Okay. A ray, like the rays of the sun, is part of a line that consists of one endpoint and all the points in the line on that one side. So if we took an entire line and said, let's start at this point right here, make it an endpoint, get rid of the rest of the line here, but in this direction, go through B and on forever, that would be a ray. Now, we can read this ray AB and we write it with the endpoint at the start underneath the side that does not have an arrow on it, and then going through B and the arrow passes past B for forever. Okay? The order of the points indicates the ray's direction. It's going from A at the endpoint through B. And opposite rays are 2 rays that share the same endpoint and form a line. Essentially, if you took a line and took 3 points along that line, and along that line you said, okay, let's kind of separate this here into 2 figures. This is an endpoint C, and we run through A, going in that direction, and another figure with an endpoint C running through B in that direction. Those together form a line, and they're called opposite rays. So we always start with the endpoint first. So we start with C here running through A this direction. Notice that it starts at C and runs through A to the right because we always have the endpoint as the left letter. Even though it's pointing in that direction, we're going to always do it that way. And C running through B, so ray CB. Together, since they have the same endpoint and they're running exactly opposite each other to form a line, they are opposite rays. Okay, so let's name the segments and rays in this figure right here with points D, E, and F on this line. And we can say, okay, what are the names of the segments? Well, let's just trace the unique segments here. We could go from here to here. We could call that segment DE, or start at this endpoint and call it segment ED, right? DE or ED. We could also start at this point right here and go in this direction to here, EF, or start there and go backwards to this section, FE, so segment EF or segment FE. And of course, we could go the whole distance here from D to F or from F to D, that whole segment there. So we can call that DF or FD. The next question we're going to answer is, what are the names of the rays in the figure? And how do we know if we're going to name all of the rays? Well, we have endpoints at the end of each ray, so let's go to each point right here, and from there go in each direction and see if we can name a ray. So from here, D, we can't go in this direction, but we can go this direction. We can either say DE or DF, it's the same ray, same endpoint D, and passing that way. Okay, so DE, also known as DF, and sorry if I'm covering the figure, I'll just pull it all off. We could start at this endpoint and go this way. We could go to E, ray ED, or we could start at endpoint E and go through F. So ray ED and ray EF are two different rays. They're opposite rays, in fact. And we could start here. We can't go here to find a ray because there's no, we do have a ray there, we just don't have another point, so we can't name it with the second point that it runs through. But we can go this way and we can say F, ray F, either ray FE, passing through E, or FD, passing through D. They're the same ray because they have the same endpoint, F, and running in the same direction. We're just naming a different point that they're running through. And finally, which of the rays in part B are opposite rays? Well, again, we need to find an endpoint that has a point on both sides of the line so that we can start at that endpoint and run in both directions. And as you can see, the point in the middle, E, we can start here and say ray ED and go in the opposite direction from the same endpoint E, ray EF. So we can say the opposite rays are ray ED and ray EF. And notice that I'm naming what it is. I'm not just saying ED, because we don't know if we're talking about a line, a segment, or a ray. So we have to say the word ray, ray ED and ray EF. Okay? Now here's your got it problem. Okay, well, we also have, besides terms, we have postulates, otherwise known as axioms, which is an accepted statement of fact. We will make a statement that we will treat as true all the time as long as it fits the right requirements of the postulate. Okay? Postulates, like undefined terms, are the basic building blocks of the logical system of geometry. We're going to be able to build from this idea a bunch of other ideas. Okay? And we're going to use logical reasoning formally in Unit 2. Okay? Now, you've used some of the following geometry postulates in algebra. For example, we used postulate 1-1, I'll get to that in a second, when you graphed equations such as y equals 2x plus 8, okay, last year in Algebra 1. You graphed 2 points and then you drew a line through those points, because the postulate says through any 2 points there's exactly one line. So when you were graphing this, if you had 2 points, you knew you were going to get the line right because there's only exactly one line through it. Line T, otherwise known as line AB or line BA, okay? Line T passes through points A and B. Line T is the only line that passes through both points. Now I can name it different ways. I can name it line AB or line BA, but it's the same line. Now, when you have 2 or more geometric figures, the intersection, the place where they cross, if they indeed do cross, which they don't always, will be the set of points that they have in common. And those sets of points will be different depending on the figures that might be intersecting. But in this case, when you have these 2 distinct lines intersecting, they intersect at this one point. That's the one point of intersection. And in algebra, one way to solve for a system of 2 equations is to graph the lines. And if you graph this and this, you will see that they intersect at this single point, which is 3, 2, and this is actually the solution that makes this equation and this equation true when substituted in for x and y. And that illustrates this postulate right here, 1-2, which is if 2 distinct lines intersect, it says if they do because they won't always, they could be parallel, or they could be skew. We'll learn about that later. But if 2 distinct lines do intersect, then they intersect at exactly 1 point. Now it says distinct lines because if it was exactly the same line twice, then they would share all points. So they're distinct different lines. They'll intersect at exactly 1 point. So these two lines, line AE and line DB, they intersect at point C right there. And there's a whole related idea for planes as well. Okay. Postulate 1-3 says if two distinct planes intersect, they're going to intersect in exactly one line. You can see that this is a representation of the plane. The plane actually goes forever in all directions, and you can visualize that. And so therefore their intersection will be infinitely along this line. Okay, plane RST, this is right here, and plane WST right here, they intersect at line ST. Notice that they both have ST in their names, and that's the line that they intersect at. Okay? When you know 2 points that two planes have in common, we know that they share S and T, then this postulate and postulate 1-1 will tell you that because there's a unique line through any 2 points, that the line through those points is that line of intersection of the planes. Neat. So if they share S and T, we can say line S and T is where they intersect. So let's right now find the intersection of 2 planes. This figure in this question will help us understand how. Okay, each surface of the box represents a part of a plane. Remember, the plane goes on infinitely forever, so this is just a representation of a portion of it. Okay, what is the intersection of plane ADC and plane BGF? And we want to just think about what we know. We know that we're talking about these 2 planes, and what we need is the intersection of those planes. So we need to find the points that the planes have in common, because finding points that the planes have in common will allow us to name the line of intersection. So what we should do then is we should focus on plane ADC in the drawing and plane BFG in the drawing to see where they intersect. Now, where do they intersect? We can see that right here, both planes contain B and C. They both touch B and they both touch C, and that therefore line through them is the line of intersection. So the planes intersect at line BC. Nice. Here is your got it problem. We will stop and answer this, and then check your answer once you are ready. So in the real world, there's a great example of this, which is the tripod. Photographers use 3-legged tripods, and 3 is the magic number in this case to make sure that the camera is steady. You will notice that 3-legged items, maybe a stool or a tripod, won't wobble. But if you have a 4-legged chair, you might get a wobble if that 4th leg is not all on that same plane as the other legs. Or what I should say is that any 3 legs can form a plane, and the 4th leg also needs to be on that same plane as the other 3 in order to not wobble. If it's not, then you can pick any 3 legs and make a plane, but the other leg will not be on the same plane as the other 3. And that suggests that any point is on multiple different planes, and I'll do an illustration of that. Now, photographers use 3-legged tripods to make sure that a camera is steady. The feet of the tripod all touch the floor at the same time. You can think of the feet as points, 1.1, point 2, point 3, and the floor as the plane. As long as the feet do not all lie in one line, they will lie on the flat, unique plane of the floor. And you can imagine that if we moved this leg in so that it was all on a line, the tripod would not be stable anymore. Okay? And this illustrates postulate 1-4, which is through any 3 non-collinear points, if they're not all in a line, there's exactly 1 plane. And again, as I said earlier, if you take any 3 points and you connect them to form a triangle, that triangle is a portion of the plane that those 3 points lie on. Okay, so points Q, R, and S are non-collinear. They're not all in the same line. So plane P, we don't have a point associated with P, so that's the name of the plane. Okay, P is the only plane that contains all of them. Now, there are other planes that might run up and down through these two, or a plane that runs like this through these two, or through these, but not through all three without being the same plane. Okay, so we're going to try to use postulate 1-4 to identify planes that contain certain points. Use the figure at the right. For A, what plane contains N, P, and Q? Here is N, here is P, here is Q. Okay, and you could shade the plane to figure it out. Now, where is that plane? Well, if we want to figure out how to find it, we can say, okay, let's draw lines through it, and I can take lines and connect N and P, and I could connect P and Q, and I could connect N and Q, like that, and then you start to see part of the plane. You see that triangle that's there, that's part of the plane. So, plane at the bottom of the figure contains all of those points. Let me erase my marks so we can start fresh again. And this is a good question because it's a little bit tricky. But let's take a look. What plane contains points J, M, and Q? So where's J, where's M, where's Q? Here's J, here's M, and here's Q down here. Now it doesn't appear maybe to you that they share a plane. However, if we were again to do the same task that they told us to do before, which is to connect the points, we can say let's connect J and M, let's connect M and Q, and let's connect J and Q. And you can start to see that there is a plane that's running this way down through all of them. Okay, so that plane exists there whether you realize it or not, whether we have a side to the box or not. There's an imaginary plane. There's imaginary planes cutting through everything at all angles. And so as we see, there is this plane that passes through here, and it seems tricky because it's at an angle and it's not one of the sides of the box, but you can now see it and imagine it, that there is a flat surface that would connect all three of those points and contain them. Yep, so here's your got it problem, and we'll stop here so you can answer it, and then you can check your answers when you have your potential answer. All right, and that's our starting point for geometry, points, lines, and planes. You can try your hand with this lesson check, answer these, and then restart the video to check your answers against what's posted. Good luck.